My name is Serkan Girgin. I am an associate professor at the Faculty of Geoinformation Science and Earth Observation of the University of Twente. I'm also head of the Center of Expertise in Big Geodata Science. So at our center, basically, we are focusing on big data and cloud computing techniques and technologies, as well as infrastructure to process large geospatial data sets, including Earth observation data. Earth observation data actually is becoming more and more available, and it is getting also quite big, more than it can be downloaded and locally analyzed. We have a lot of Earth observation satellites and the constellations that are available, which are continuously collecting Earth observation data. And publicly available data archives are getting bigger and bigger, which is actually quite nice because it enables us to analyze large spatiotemporal extents of data. Nowadays, it is becoming more and more common to see studies where people are analyzing 40 years of Earth observation data, starting from Landsat archives and combining it with the Sentinel and Copernicus data, for example. And we are also seeing a lot of global extent studies, which were quite difficult to do in the past. So nowadays, they are relatively more easy to do because we have some infrastructure and capabilities available for that purpose. Still, accessing large amount of data takes significant amount of time and also effort, especially if you are using web portals and manually select the images and download them one by one. Data processing and analysis tasks also takes a lot of time. We are having more resource-intensive analysis techniques like machine learning, deep learning, AI type of work. And they take significant amount of time, especially if you do the analysis on your laptops or local workstations that you have. Sometimes we can even say it is not possible to do the analysis. So you start the analysis, you start waiting, and after several hours, you end up with an error. So you cannot compute what you want to do. But still, this is the most common way of analyzing Earth observation data. So we see a lot of people downloading the data, trying to find a more powerful laptop, a more powerful server at their institutions, and try to analyze the data or dividing data into smaller parts so that it becomes manageable. Actually, cloud computing enables several solutions to this problem. When we talk about cloud computing, basically, we talk about on-demand availability of computer system resources, like CPUs, memory, or storage capacity, without direct active management by the user. So we don't interact with a human being. We just go to the service provider's website, we request the type of resources that we want, and most of the time, immediately, we get those resources. We can determine the capacity that we are interested in, and we can easily scale up if we need more processing capabilities, or if we are just doing some prototyping, we can also scale it down. So it's quite flexible. If local resources that we have are not sufficient, then using this kind of cloud-based resources like virtual machines is actually a solution that we may have. But if we do this, basically the type of processing that we do is not different from local processing. We still need to download the data from a data provider. We still need to create our computing environment. We need to install packages. We need to write our own scripts, usually in common programming languages. So we are only changing the machine that we have. Instead of having a physical machine, we are using a virtual machine. This may solve the problems up to a certain point, but especially if you need to process large amount of data, then another solution cloud-based systems can provide is in fact infrastructure where the data is already located. So nowadays, we have public cloud providers like Google, Amazon, Microsoft, which have a large amount of Earth observation data archives, which they keep regularly up to date. So by using their infrastructure, you can access Earth observation data easily. Even better, we have some cloud service providers specialized on Earth observation. Some examples from Europe are, for example, European Space Agency's DIASS. They provide specific infrastructure that has the complete Copernicus archive, for example. So in that case, the data is there. You don't need to download the data, but you still need to set up your computing environment. You still need to install the packages. You still need to do computing relatively manually. So one example of this kind of systems is, in fact, the innovation lab that is provided by the EU Africa R&D facility, which we are using during our online courses, face-to-face courses, and probably some of you had attended or maybe are planning to attend such activities, and there you will be using the innovation lab. And you will see that the complete archive is already there, so you don't need to download the data. This enables also co-located data analysis, and because the data is located where the computation is taking place, you can also get the results relatively quickly. One step further of this is, in fact, cloud-based platforms, which are specifically designed for Earth observation data processing, which provide access to data. That means the data is located there, but at the same time, they provide an infrastructure, a computation platform that is dedicated for Earth observation data analysis. So that means you don't need to install your own packages. You use either the API, so the programming interfaces that are provided by these platforms, or you use the visual programming environment that is provided to create your workflow. You don't need to deal how the computation is taking place. Everything is handled by the platform, so you can focus on the type of analysis that you are interested in. A good example, and in fact, the most famous example of such a platform is Google Earth Engine. Google Earth Engine has been around for a lot of years now, and it is considered as a game changer because it enabled for the first time a multi-petabyte level of data catalog, which includes a very rich amount of data sets, which are also kept regularly up to date, together with a planetary scale geocomputing capabilities available for free up to a certain point. So in fact, it enabled for a large group of people to analyze the data easily and also to analyze the data at the continental or even at the global level. Of course, it's a very nice system, but one issue with the Google Earth Engine is that the users can execute the commands, the functions that are available, but they don't know exactly how the computation is taking place. So the system is not transparent, the source code of the functions are not available, and you can also not modify the functions. So as long as you use what is available and you don't care how the computation is taking place, then this might be acceptable. But the problem is, now we are in the era of open science, and open Earth observation science means that just using open data is not sufficient. We also need to know transparently how the computations are taking place so that they can be replicable and reproducible. In fact, some time ago, around 2016, a group of researchers from different prominent research institutions, mainly from Europe, together with some infrastructure operators, like Google and a Joint Research Center of the European Commission. And they start to discuss about this. So this transparency issue, the open science approach, but at the same time, the existence of many different platforms, which are basically providing similar computing capabilities, similar type of data, but by using different interfaces, different functions, different commands, different user interfaces, which people need to learn individually. In fact, they find this very similar to the situation where we had with the GIS software around 1980s, because at that time, open source software were not very much common. Most of the GIS software were in fact closed source, and those software, they had their own implementation to read the data, to do the processing. So it was almost impossible to know how the systems are reading the data and how they were doing the computation. But this changed quite drastically thanks to a library which is called GDAL. So most probably all of you heard about it, because basically it is the foundational block of the GIS software nowadays, both closed and open source. And in fact, what GDAL did was to provide a standard library to read a large number of raster datasets initially, which was extended later also with vector datasets. And by using GDAL, it became possible for other software to read all those files easily. And that led up a significant improvement also in the GIS software, especially in open source. So the group of people basically had the question, okay, how can we make something similar also for Earth observation data processing and bring these isolated data center efforts and also the isolated platform development efforts under a single umbrella. And learning from the past experience, especially from GDAL, they came with the idea to develop a GDAL for Earth observation analytics, which they called OpenEO. So they have a very nice open white paper as a blog post, which is available in the link on the slide. So I highly suggest you after this webinar to read this white paper to understand the motivation behind OpenEO. They applied for European funding for that purpose, and in 2017 they got a Horizon project to develop the system. The system, which they call OpenEO, allows users to connect cloud-based Earth observation data analysis platforms in a simple and unified way. So in the traditional approach, there are different clients. From clients you can think of like a Python package, a R package, or a desktop GIS application. And in order to do the computation, they had to connect different backends. And because each backend has a different implementation, they had to also replicate this functionality in their own software. So in case of OpenEO, this communication is handled by OpenEO API. So it provides a standard interface and a specification which the clients can implement. And by implementing this, they become compatible with OpenEO. And the backends also similarly, when they implement the OpenEO specification, they become suitable to serve the clients of OpenEO users. So it really brings platform providers and the service providers together with the users coming from different domains. So how does it work? So basically, OpenEO API provides a contract between clients and backends that describes how they need to communicate to each other. So each backend runs its own API instance, including a specific backend driver, which I will explain in the coming slides. And the clients, which are written in different languages like R, Python, or JavaScript, they connect directly to the backends and communicate with the backend by using the HTTP protocol and a JSON-based file format. So that means the client side, the local computer that you use, only describes what needs to be done. And then all the computation is taking place on the server side. The server gets the recipe that you ask for, it analyzes it, it creates the necessary workflows, retrieves the data from its local storage, performs the computation, and then returns the results back to the client. So all data access and processing occurs on the server side. The benefit is there is no data transfer except the results that are coming from the server. And because the data and the computation is taking place on the platform side, it is also quite fast. So OpenEO API basically defines this standard service interface. It is based on OpenAPI standard. So that means the specification can be read by any system that is compatible with OpenAPI. So it's relatively easy to develop software based on OpenEO. The specification does not try to reinvent the things. So it is using existing standard methods, for example, for authentication, for data cataloging, for file formats or coordinate reference systems. It adopts the model of cube view, which means regardless how the Earth observation data is stored on the server, they are analyzed by using regular grids in a specific coordinate reference system, and usually by using a regular time interval. The system adopts a lazy evaluation, which means the computation is not taking place immediately. It only happens when there is a need to do the computation. So for example, you can describe which data you want to read, what kind of analysis you want to do, what type of output you want to have at the end, and only if you request the result, for example, by asking to download the output, in that case, the system starts to do the computation, which saves a lot of time, especially for development purposes. The system is capable of reducing the dimensions. For example, you may have a red band image and a near infrared image. And by combining these two images and doing a reduction by using NDVI equation, from two images, you can get one single image with the same dimension. So here we are reducing the number of bands. Or similarly, if you have a time series of, for example, 10 years, then you can take this time series data and calculate the trend slope by using, for example, linear regression. So in that case, the single value that you get as a slope is also a dimension reduction. Similarly, the system is capable of also doing aggregation. For example, you can indicate a region, and based on that region, you can compute some spatial statistics. So these are all things, functions, methods, and processes that are defined in this specification. In order to perform the tasks, OpenEO API has several components. So for authentication, it supports basic authentication by using HTTP protocol, or you can use OpenID Connect, which I will show you later on. It has a system for account management, so handling user profiles, accounting, and payment, because OpenEO is an open software, but the backend operators which run services based on OpenEO don't need to provide these services for free. Most of the platforms, they provide it for free or for free up to a certain computation level, but usually afterwards you need to pay. This is how basically the systems work. So the specification is open, the software is open, but the service itself may not be free. Then there are endpoints or components for listing the capabilities, searching for data, asking for what kind of processes can be done on the backends, sending this processing requests, which we call jobs. And there is also a component for file management, which is mostly used to save your own assets, which you require for computation, or to save the resulting data out of the process. If you are interested to look more in detail the specification itself, you can have a look at it interactively. So you just need to go API openeo.org, and there basically all the specification is available as a web page where you can move from one component to another. Due to the sake of time, unfortunately, I will skip this, but I can do it maybe during the Q&A part of the webinar. The backend drivers, which basically is the low-level platform software, implements this OpenEO API by using different technologies. So basically, there is a backend driver which is using JupyterLab. JupyterLab is a system which is based on Apache Spark, so it is designed to process big data sets. And JupyterLab's backend is using the Spark technology to process the data. Similarly, for example, there is another backend which is based on Grass. So Grass is a desktop GIS application, as probably most of you know. And there is also a web version of Grass that is available. And in fact, Grass GIS backend is using Grass to do the computation. Similarly, there are backends for Google Earth Engine, for Open Data Cube, for Apache Airflow. So eventually, these are all software components that are developed mainly by prominent Earth observation, either research or application institutions, and they use these backend drivers to provide the services. Backend drivers are usually quite complex software. So because in order to implement the OpenEO API specifications, they need to find a way to store the data, and that data storage normally should be compatible with big data. So that means they need to be able to efficiently manage sometimes petabyte level data, which is really complicated. They need to find a way to do the computations, and they also need to be able to provide the catalogs. They need to be able to store the metadata about the operations that are taking on. They need to find a way to store user information. They need to keep track what type of resources are used so that they can create a kind of either a log, or they can provide a kind of billing at the end. So they are really complex, but all of them are open source. So that means if you are interested, you can go to the code repositories and you can see the details about how these backend drivers are operating. By using these backend drivers, different institutions, they operate backend services. So services are the implementation of these backend drivers. So that means there is a IT infrastructure, which is composed of a certain number of computing nodes, a large data storage system to hold the Earth observation data, and the backend driver software is running on this IT infrastructure most of the time in a distributed manner. So that's why it requires significant resources. There are several backend services or service providers that are available. And actually, the list that you see is the complete list of backend service providers. So if you want to use OpenEO, you need to choose one of these backend service providers. We have recently Copernicus Data Ecosystem, which is funded by European Space Agency. But in fact, most of the platforms in the list are either supported by European Space Agency or they are supported by European funding. So probably you will see some familiar names like Vito from Belgium or Sentinel Hub, which is basically operated by Synergize. They are providing OpenEO services, but in fact, they have also additional services, which maybe you are already using, like the Sentinel Hub enables a web interface to access the data. OpenEO platform, which is indicated close to the end, is relatively a new initiative. What makes it different from the others is that the OpenEO platform is a federated platform. So which means it is not a platform by itself, but different service providers, including the Sentinel Hub, Vito, and EODC, they provide their services also through this OpenEO platform. And in that case, you don't need to choose a specific backend service provider, but you just connect OpenEO, and ideally, and this is under development, the system automatically sends you the proper or most suitable backend for your computational needs. In order to get a list of these service providers and what type of services that they provide, there is OpenEO Hub. That's also a web page. So if you go there, basically, you can see all these service providers. You can see what type of services that they provide and what type of processes they support. In order to use these services, you need to use an OpenEO client. And this client basically allows users to access the services that are provided by the backends. Clients are available in different languages. There are 3 languages that are officially supported: Python, R, and JavaScript. So that means you install the packages of OpenEO in the language, for example, in Python, and then you write a Python code to use those services. An example is given on the slide, for example. The clients, but not limited only to programming languages, there is a client available for QGIS, which enables you to connect OpenEO backends through QGIS and send the queries and get the results back into the desktop application. And they also developed a web-based interface, which they call a web editor, which enables you to create workflows without programming, but only by connecting different nodes together in an easy way. So it's an interactive programming, we call. And at the end of the webinar, I will give a demonstration, short demonstration by using the web editor, actually. So this is the architecture of OpenEO and basically the components that you should know and the terminology that you should be familiar with if you want to use OpenEO. When we come to the actual computation and how it is taking place, then basically the atomic building block, so the minimum building block for a workflow is a process. A process is an operation that performs a specific task on a set of parameters, input parameters, and returns a result, an output. You can think of as a function in common programming languages. So if it is, for example, in Python, if you write a function, you indicate the input parameters, and then you return a value, usually at the end. So the concept is similar. Predefined processes are the processes that are made available by the backends. So they come out of box, they are available. And there is a list of centrally defined OpenEO processes for common tasks, like, for example, summing 2 bands, dividing them to each other, for statistical analysis, like calculating the mean or taking the maximum, and also some processes that are specific for image processing, like masking a layer or applying a kernel. a moving window for averaging or for different purposes on the spatial level. So the backends are expected to support these centrally defined OpenEO processes, which are called standard processes, but they are free to define their own as well. And also, they may, from time to time, deviate from the standard description of these processes. That's why it is always important to check if the backend that you are using supports the functions that you are interested in and up to which level. For that purpose, there is a kind of discovery service available, and that service allows you to see what type of processes are supported by the backend that you're connected to. It is possible to combine multiple processes, link them to each other, so creating a chain, and storing them under a user-defined process. So this allows you to build a library of reusable components that can be inserted to different places in the workflow. So for example, while writing a Python script, you write your own function, but in the function, most of the time you call other functions that are available. That's the same idea. You use the standard processes, you package them under an umbrella, and you call it a user-defined function, and you can use it whenever it is necessary. Available OpenEO processes can also be listed interactively. So processes.openeo.org webpage provides you the list of processes. There you can browse what type of processes are available, the description of the process, the input parameters, and what is the standard output that is coming from the process. These processes, as I mentioned, are the building blocks, but in order to create the workflow that you are interested in, you connect them to each other. And this connected processes forms a process graph. And each process in the graph is named as a process node. It is possible to use predefined processes or the user-defined processes to create a process graph. And in fact, a user-defined process, because it's a collection of processes, is itself a process graph. So eventually, everything turns into a process graph. Similar to the common programming languages, basically, the process graphs allows you to organize and automate execution of one or more processes. And they described basically how the inputs and the outputs of a process should look like. So let me give you an example. So here we have a calculation process graph. It has three components. The first component is to load data. So here we indicate the spatial area that we are interested in, which is a bounding box. We indicate the temporal extent we are interested in. We indicate which bands of data we want. And then the result of this process is a data cube, which includes the data for the area that we ask for the temporal range that we ask for, from the satellite or constellation that we are interested in, which will only contain the bands that we ask for. This data could be quite big. So we can do some dimension reduction on this data. So if you have a time series and if you want to, for example, remove the clouds, is to take the median value, right? So in that case, you can create a dimension reducer, which use the arithmetic operation mean, which will convert, for example, 10 different images into a single image. Or similarly, as I mentioned before, NDVI is also a reduction operation because we have two bands In this case, it's a red and near infrared band 4 and band 5. And from this, by using a mathematical, we create a single band. So the reduced dimension process takes as an input the initial data cube that we get, and it returns as an output another data cube, which has only one band with the values of the NDVI equation. Then, in order to get the results, we have the last process, which is the save results process. This process allows us to save the data cube in a format that can be read by GIS or remote sensing applications. In this case, it's a GeoTIFF. And at the end, we download the data. And in fact, if you look at this reduced dimension process, that process composed of a collection of processes. We take the data, we separate the data by taking each array element, so band, first band and the second band. And then, as you know, the NDVI equation is near infrared minus red divided by near infrared plus red. So in the first box, which is called add, we see these two bands that are added together. In the second one, we see them subtracted from each other, and the last process box divides them. And actually, this is how you describe the NDVI operation by using OpenEO. Of course, this may sound a little bit complicated. So because normally NDVI is a basic operation, but in order to create the NDVI, we really need to put a lot of processes. We need to link them together. By using user-defined functions or user-defined processes, of course, we can create an NDVI process and we can put all these sub-processes under it. But another way to extend the capabilities of OpenEO is also to use user-defined functions. So, and user-defined functions allows you to upload your custom code, which will be executed for each pixel in the data cube. So this allows you to do the computations on the server side that are either not covered by the available predefined processes or the ones which may not be easily done by these processes. If the algorithm that you want to run is really complex, then using the processes and combining them together really may not be very easy. But writing a Python code might be much more easier. The challenge, of course, in this case, then basically the backend needs to deal with it. So the backend should support user-defined functions. And there is no performance guarantee, and sometimes also no guarantee of the operation to be done in an efficient way, because the code is arbitrary, so it's very difficult for the system to optimize this. Creating a process graph, as I mentioned at the beginning, is a lazy operation. So unless you ask for data downloading, nothing happens. And this the point where something starts to happen can be in two different ways, either synchronous or asynchronous. The best way and the suggested way to do the computation is to create a batch job. So in that case, you create your graph, you create a job to process this graph, you submit it to the backend, and the backend takes your graph and puts it into a process queue, which serves all users that are connected to the backend. So that means you start waiting for the computation to take place. But the good thing is, once your graph starts to be running, you have usually access to a significant amount of resources, and the computation can run for a long time. So by using these jobs, it is possible to send processes which can take hours, even days. So that is possible. The results are stored on the server, and then you can download them or you can use them as an input to another process or another job that you submit. These type of jobs are usually for time-consuming jobs, and interaction is not possible once you submit the job. You can query the status, you can see if the job is still in the queue or start running, but until it is completed, basically it's not possible to know how much of that process is completed. But still, it's the only one which can give you an estimate before you start the computation about approximately how much time it will require, how much data volume storage it may require, and if it is a paid system, then it is also possible to get an estimate about the costs, if that is supported by the backend. The second way to submit the data is on-demand data processing, which we call synchronous. In this case, when you submit your request, your process graph sent directly to the server. No job is created. The system automatically starts processing your request. But this kind of process running is only available for lightweight computation because the system communicates through the HTTP protocol, and depending on the timeout that is set by the operator, it can only run for a few minutes, but not longer. And after that period, usually you get the timeout, so you lose all the computation up to that point. And most of the time, you cannot get also the results out of it. It is only suitable if you are working in a small area. That means the computation finishes quickly, or you use some basic operations like getting a preview of an image instead of doing the actual computation. So for this kind of task, it is really suitable. The best way to have some experience, hands-on experience with the OpenEO is to use the web editor, which enables you to create interactive workflow-based processing graphs by using OpenEO. You can use the editor.openeo.org to get connected to the web editor, or you can use the web portals of the backend providers, because most of the time they also provide a web editor interface. And actually today, in the demonstration part, I will be using Copernicus Data Space Ecosystem, which is a project funded by European Space Agency, which is also the funding agency of EU Africa R&D facility. There you can create an account for free. And for each month, you also receive a certain amount of credits, which enables you to do Earth observation data analysis for free. So any questions so far? So if you have any questions regarding OpenEO, the components of OpenEO, I can have a quick answers. Otherwise, I will show you how the web interface works. Okay, so it looks like there are no questions. So I will now do the demonstration. Do you see the web page? Okay. So once you go dataspace.copernicus.eu, it enables you to explore the data through web interfaces, or you can also analyze the data by using different means, like by using JupyterLab or using Sentinel Hub. But one option that they provide is OpenEO. In order to use it, first we need to log in. So I have an account, so I will just sign in. As I mentioned, you can create accounts for free. And once you log in, you can go to OpenEO. And on the OpenEO page, clicking this OpenEO button will open the web editor. So in the web editor, basically on the left-hand side sidebar, you can see the collections that are available on the backend. So these are the data sets. To provide access to the data sets and to query the data sets, OpenEO is using Stack standard, which is spatial temporal asset catalogs. That's also a relatively new way to query data. And you can also see the processes that are supported by the backend. As you can see, there are more than 130 processes that are available. You can also see that the system allows you to create user-defined functions in Python. And it supports also a set of file formats like netcdf, geotiff for raster data, and GeoJSON, Parquet, or covered JSON for vector datasets. On the right-hand side, basically, we have the editing window. And by selecting the process that you want, and by using a drag drop, you can put it on the workbench screen. By clicking the item, you can open the properties. In the properties, depending on the process that you are editing, the system gives different parameters. They are nicely documented most of the time. So here, for example, this load collection process has the spatial extent, it has the temporal extent. So for example, we are right now located in Netherlands, in Enschede. So if I want to get the data for Enschede, I just click. By clicking there, a box becomes available. By dragging and dropping the boundaries of the box, you can change the spatial area that you are interested in. Then the second parameter is the temporal extent. In case of temporal extent, by default, the system gives you the starting date of the collection. So this is Sentinel-2 collection, and Sentinel-2 collection starts in 2050. But if you are interested in more recent images, for example, from 2024, then you can select. Let's say we are interested from July, and from July 15, we want to get images until the end of July. So basically for 15 days. Then another property that you can indicate is the bands that you are interested in. By clicking add, you can add more bands. And by selecting the list box, you can also choose which band you are interested in. So, of course, sometimes it is not very clear what band 4, band 8 means. So, in order to know what they are, all you need to do is to go to the collection part, clicking the name, and then the system automatically gives you a description. So we are looking now Sentinel-2 level 2A. The spatial extent is global. Temporal range is starting from 2015. We have information about the data providers. We have information about the spatial resolution. And we have also a table of spectral bands from which we can see what the meaning of this B4 or B8 is. So B4 is in fact a red band, and B8 is the near infrared. So these bands and the data collections that are available are not standard. So OpenEO does not enforce the backends to use a specific naming convention. Depending on the backend that you connect to, you may have different names, you may have different spatial extents that are available. So in certain backends, you may not have global data, but maybe data available only for Africa, or maybe only for starting from 2020, for example. Or the naming of the bands might be different, and also the data type of the bands might be also different. So in case of Copernicus data ecosystem, all these bands are integers. And in order to convert this to actual values, you need to multiply them with this scaling factor. But in a different backend, this might be different. So that's why you need to check always the data description and modify your workflow if necessary. Okay, so now we have the selection one. And now the minimum that you can do is in fact to retrieve the data and download it. So for that purpose, we have the save result process. We drag and drop. And in order to connect these processes to each other, we take the result and we connect it to the input of the process. Now, before I did the connection, actually data was also indicated in red, and red means there is information which is missing. And in fact, I still see the format is missing because I didn't choose the format, and this is something I should do. I click, and then here I select the format that I am interested in. For example, let's say I want a GeoTIFF. If I select GeoTIFF, the system also provides me some options which I can select. You can choose the compression level, you can choose the color map, and these kind of things. For the time being, let's accept the default values. And now we have our first OpenEO process graph, which we can run. In order to run, of course, I need to log in. So I click the login. The system will ask me if I want to log in with my Copernicus data system ecosystem credentials. I click yes. Because I already logged in, the system will take my authentication and it will go back to the web editor. So now I have a second section under the workbench window, which is about running the process. So as I mentioned during my presentation, there are two options that are available. You can run it now, which is a synchronous way of running the processes. As I mentioned, this will run only if the analysis is something quick. Here, I choose a very small area and the time period is also small. So our expectation is that it will be fast. So that's why I will just click run now. And now, as you can see, I see a notification which says a process is currently executed synchronously. So now my process graph is sent to the backend server. The backend server encoded the process graph. It identified which data it needs to retrieve. It looked at the catalog. It identified the Sentinel-2 scenes that are overlapping with the study area that I choose for the time period that I choose. And then it did the computation. And as you can see, it opened two things. So one thing is this, maybe actually we can do like this, a map. And on the map, basically it displayed the GeoTIFF that I have. Of course, because the values are integer. So here actually, as you can see from the pixel value is quite large. And because it's quite large, it goes beyond the RGB range of a visible image. So that's why we see it as white. But if I open, for example, QGIS, and then open the file in QGIS, let me do it quickly. Then here, you can see the result. So this is the image that I get after processing. So I have two bands, band 4 and band 8. But I see some issues on the image, right? So normally my expectation first of all, let's say questions to you. So please try to answer. You can type also in chat, but maybe you can also tell me directly. So do you expect to have a single image for 15 days from Sentinel-2 for a specific area? Or should there be normally more than one? Any ideas? So normally our expectation is that we have multiple images because first of all, as you can see from this image, the Sentinel passes not exactly over Enschede, but from south, from east and west. So that's why there are two different scenes that are overlapping on Enschede. And because of the period of Sentinel, we have also multiple passes over Enschede within 15 days. But here I see a single image, and that single image is a little bit mixed up because basically the data format that I ask for, which is GeoTIFF, supports only one band, one image for each band. So the system had to merge multiple images, and because I didn't indicate a clear way to do it, it just mixed the images. So that's why I received something like this. One way to solve this problem is to use a file format which supports multiple bands. So I will click this Save Results, and I will change this to netcdf. And I will run it now. So netcdf is a multidimensional file format, which is very common actually for earth sciences, especially for meteorological, climatic, and water resources type of work. The difference between GeoTIFF and netcdf, in case of netcdf, we can have a detailed description of the dimensions. It allows metadata to be stored. It means a machine-readable metadata to be stored with the data, and it is also multidimensional. So that means it can store multiple bands in the same file. So that's why now it will be possible for me to receive all the bands in a single file, which I can also open in QGIS. So now I will go and I will open the netcdf file. So if I open, for example, band 4, now in this case, if I make it single band gray, so as you can see, I have 7 different bands, and each band actually corresponds a different day. And by selecting corresponding day, I can access the data that is available at that day. So as you can see, for this day, I have a complete image. For this one, I have another one. And as you can see, the amount of clouds are different. The view is different because it is from a different time period. So this is the way to create a OpenEO process and get the data. But of course, our intention is not to download the data. So as I mentioned, this is a kind of a traditional approach, downloading the data and processing locally. What we are interested in is to perform a computation. So for that purpose, what I will do is to use a nice feature called Wizard. So by using the Wizard, you can create a workflow very easily, a predefined workflow very easily by using the web editor. There are not too many options available, but it provides you a good start. So I will select this compute spectral indices. Once I select the indices, the system will ask me which data. So here you can see the steps at the top. The first step is the selection of the data source. So I will select Sentinel-2A. Then the system asks me what type of index I'm interested in. So many different indices are already available, described. So we have the vegetation indices, we have water indices, we have soil indices, and the system can automatically calculate all of them for you. You can also search. If you are interested with NDVI, you can enter NDVI, and then you can easily find it. Let's select. Then it asks me which area I am interested in. Let me go and scale again. I'm clicking the area because our university is located here, so that's why I am interested in that area. We have also some water ponds, which will actually give a nice view in the NDVI. Then I click next, and then I can do the same. I can select the time frame that I'm interested in. Let's go to this year, July, from 15 until, let's make it maybe 22, a shorter period. And then the system asks me if I'm interested in a temporal composite. So as you saw in the case of netcdf file, when I indicated the area that I'm interested in and the temporal period, the system provides me all the images that are available. And similarly, if I do the NDVI computation, it will calculate these NDVI values for all image individually. And at the end, if I download it as a GeoTIFF, it has to mix everything, so it becomes quite mixed. One way to solve this is to reduce the data, this multi-dimensional in the temporal range data into a single image. And for that purpose, we can do a temporal composite by using a reduction function. We can say we are interested in minimum value, we are interested in maximum value, or you can say, okay, I want the median. And if you click median, it becomes available. And then you indicate the file format that you are interested in. So let's say, because we are doing the temporal reduction, we can use GeoTIFF. If you want to create a JPEG or a PNG file, then you also need to scale the values, because normally NDVI is between -1 to 1, but a JPEG, a PNG RGB, it's between 0 to 255, so that needs to be scaled, but we are interested in GeoTIFF, so that's not necessary. You just click next, and then the system gives you the option to run it immediately, to run it as a batch job, or you can say don't execute. And if you say don't execute, the system will only create the graph. This is very nice because basically you can edit. You can create your process graph by using the wizard, but then by clicking the process, you can change. For example, I can change the spatial extent that I am interested in. By clicking this reduced dimension, I can also see how the NDVI computation is created by the system. As you can see here, we have the reduced dimension process, which has a kind of a sub-process in it to calculate the NDVI. It is separating two bands. It is adding them together. It is subtracting them together, and it's dividing them. So as I also mentioned in the presentation, that's the standard NDVI computation. And then it saves the results as a GeoTIFF file. So now if I click run now, the system will collect the data like it did before, but then it will do a temporal reduction. It will take the median value for each band. It will create two different bands with the median values of each. And then it will use these two bands to create the NDVI by using the NDVI equation, and it will return the resulting raster, which is actually available here. So if I open it in QGIS. Here I see my NDVI. Let me zoom to it. So as you can see here, the numbers are theoretically between -1 to 1. And we can change this to pseudo color. And if we say, for example, we are interested in 0 to 1, then we can see the places which are green. So actually these parts are basically the fields around Enschede, and the ones that are indicated in red color are mostly urban settlements, and here are covered by clouds. But eventually, OpenEO did the calculation for us. It retrieved all the data and provided the results. So my machine, my laptop, in fact, didn't do anything at all. This is the benefit, actually, in using a cloud-based Earth observation processing platform. So the limitations of the computation that you can do is only limited by the capabilities of the backend. And because the backends are based on very powerful IT infrastructure, they can really process large amount of data. They are also relatively fast. So here, as you can see, we just waited a few seconds to get the results. If the area increases, of course, it requires more time. But the good thing is you don't need to wait. So what you can do, you can, by using your graph, you can create a batch job. So let's run it also in the batch job. You give a name. And once you create the job is just created. So it is not run automatically. So you need to specifically give a start processing command. Once you do that, then the system submits the processing graph to the computing backend. As I mentioned in the presentation, most of the time, it doesn't start processing immediately. It puts in a processing queue, as it's indicated. Now it is successfully queued, it's in the queue. And once the resources that are necessary for the computation becomes available, our process graph starts to run and the system starts processing. Of course, this is for small tasks, this is much slower than the synchronous request, because in the synchronous request, we ask, we get it immediately. But the good thing is, with these methods, we can run very time-consuming long tasks. You can close your web browser, you can come back tomorrow, and if the process is completed, you get the results. If the process is continuing, you will see that it is continuing. And this way, you can do Earth observation data processing at scale. Most of the time, because this kind of analysis requires significant resources, those operations are not for free. So you need to check the backend operator's website to get the information about the costs. Or you can also sometimes ask for sponsorship. So European Space Agency, through network of resources, allows researchers to apply for funding, which also includes OpenEO services. So you can write an abstract of research activity and you can apply for funding. And if you are awarded, then you can use the credits to process the data. Because ESA is supporting OpenEO initiatives significantly, there is a quite high chance for you to get funded. But in any case, all these backends, they provide up to a certain amount free credits, and this will enable you to test different things and learn how it works. Okay. So now, as you can see, my job is running. One thing that I want to show before finishing. So this is the way to create your process graph interactively. The good thing is this web editor can export this process graph into different scripts in various languages. So for example, if you click export as source code icon, and if you select Python, then the system gives you the Python code that does the same computation. So you can download this code, or you can copy paste this code. You can put it to your JupyterLab instance, for example, in a notebook, and then you can do the computation in a notebook environment. You can visualize the results, or you can get the output, but instead of downloading as a TIFF file, you can get it as a X-array, and by using X-array, you can do further processing or visualization locally. I also highly suggest you to try this. So if you are a member of a Africa R&D facility, and if you have access to Innovation Lab, you can use the JupyterLab that is provided by the Innovation Lab. Copernicus data space ecosystem, it has also a JupyterLab interface available, which you can use for that purpose. But you can also use your local JupyterLab instance running on your laptop, because the computation is taking place completely on the server side. Your laptop will not do any processing, but it will only send the request. So all of these options will perform equally. Okay. Yeah, it is finished. Now the process is finished. And if you click this download icon, then you can get the resulting output as a GeoTIFF file, or you can also copy the URL. Because we run it on the server, the output is saved on the server. So it provided a URL address which you can download. If you click download GeoTIFF, then you get the GeoTIFF, and this should be normally identical to our previous one, which is here. Okay. So this is basically how OpenEO works. I hope it was informative enough for you to have as first a step for OpenEO. Of course, it's really a kind of complex system. It has a lot of more than 130, as I showed you before, processes. So I can highly suggest you to have a look at the processes that are available, and please check also the backends. OpenEO website. Maybe I can very shortly show you. Let me show you very quickly the OpenEO website. Do you see my web browser, web editor? Yes. Okay. So if you go openeo.org, this is the web page of OpenEO. So here on the top menu, if you click software, then you can get the links to the clients that are available in different languages, as well as the QGIS and web editor. You can see the list of backends that are available. You can have the link to the OpenEO repository where the specification exists. If you click it, you go to the GitHub repository, but by clicking this API openeo.org, you can go to the interactive version of the specification. Here, as I mentioned, you can get information about the API principles, but moreover, all the type of processes that are available, how the process graphs are handled internally. And you can also get information about different components, their endpoints, and what kind of input they take. This part is mostly for developers. So as an end user, you don't need to deal with it, but just for information, I am showing this page. What is more important for you is this services and hub link. If you click that one, you will go to the OpenEO hub. On the OpenEO hub, you see all the operational backends. By clicking the name, you can get more information about the backend provider if they are production ready. So for example, this Copernicus data space ecosystem that we are using is production ready. That means sufficient resources are available for doing actual computations. But not everything is supported. As you can see, estimate processing cost is not supported by this backend. So that means it's not possible to know how much it will cost in terms of time, in terms of data storage, or in terms of processing credits. But you can do the processing. You can see all the collections that are available. You can see all the processes that are available. And you can check also similarly for other backends. The good thing is, you can also filter them. You can say, okay, show me the backends which have the basic functionality as well as the batch processing. As you can see, Sentinel Hub becomes unavailable because Sentinel Hub apparently doesn't support batch processing. Or you can say, okay, from input formats, I am interested to know which backends support NetCDF. If you select this, then you see the ones which are supporting. Okay. This allows you to find the backends suitable for your needs. Then we have the user documentation. In the user documentation, basically, you can check the glossary for the description of these processes, the collections, similar. You can also get some information about the data cubes, how they are formed, how they are reduced. That kind of information is available here. Then by selecting the language that you are interested in, you can get specific help for the client, for example, the Python client. But more importantly, by selecting the processes, you can go to the processes page, which lists all the processes that are available as standard processes. And here you can say, okay, I'm interested in aggregate spatial. Aggregate spatial provides zonal statistics for geometries. So that takes a data cube as an input and a geometry object as an input. And you can read what the input data needs to be, what type of geometries are supported. So this really provides you a nice summary about the capabilities of each processes. And the last thing that I want to show you is the cookbook. If you go to the cookbook, then you will have a nice tutorial which shows you basically how to connect a backend, how to load a collection, how to reduce the dimensions, how to save the results, doing some computations. For example, NDVI was the example that I gave. You can also do it in AVI. The good thing is this documentation is multilingual, so it shows you the code for Python. If you click R, you can see it in R, or if you want to use JavaScript, you can also get the JavaScript code. And by following the tutorials step by step, you can learn how to use OpenEO also in a programmatic way. Okay. Please have a look. I think you will find a lot of useful information on the web page. And by practicing, you can always improve your skills. So now I want to check the chat to see some questions. So if you have any questions, please post them in the chat, or you can also turn on your microphone and tell it directly. I see a question from Wubalam. So what are the comparative advantage power of OpenEO over Google Earth Engine? So that depends actually. So Google Earth Engine, of course, has a lot of data sets that are available. So if we check the backends that are available on OpenEO, most of them have a little bit more limited set of data sets. But Google Earth Engine is also available as a backend. So that means you can also use Google Earth Engine to do the processing. In that case, you have all the data sets that are available on Google Earth Engine, and you can use all the standard processes that are available and create your workflow. The good thing is that workflow will be transferable, so you can transfer it to another backend and run it there as well. So that's one of the benefits. The computation that you are doing is transparent, so you know basically the code. You know also how it is implemented because the source codes are available. So if you are willing to follow better open science principles, then I think OpenEO could be also a nice option. The limitations, but of course there are some limitations. In case of Google Earth Engine, I believe the computation capabilities are much better. Basically, as you know, Google, Amazon, and Microsoft, so they have an enormous IT infrastructure. They have planetary scale computing infrastructure. So we are talking about hundred thousands of servers that are available. That enables computation at the global scale. The development environment is also, the web interface is more advanced than the web editor that we have. But OpenEO is also relatively new development, and that is mostly developed by the research institutions. So there is also no professional software development support. That's why things might be a little bit slow, but in time, I think we will get better and better capabilities out of OpenEO. Another question from Beatrice. Which reduction function is ideal for compositing multiple bands over a period of time to reduce a cloud-free data for an area? So actually none of them, to be honest, because just getting a single value out of selected bands doesn't enable you to filter out clouds. The best way to do it is to use a cloud mask. So most of this Earth observation data, especially the ones for Sentinel-2, they come also with a cloud mask layer, and you can use that layer to filter out the clouds. I think that would be the best, because those mask layers are computed by more advanced algorithms, which takes many different information into consideration. I cannot tell that they are perfect, but at least they can give you better results other than using this mean or any other simple arithmetic. The OpenEO cookbook has a section on how to mask bands. So if you check that section, you will see how you can do it. Okay. Any other questions? Bob Sami asked a question. Same question as Beatrice, but a bit different. What is the major difference in the image you get after using median reducer or mean reducer? So basically, there are two different statistical parameters. In case of mean, basically, you get the average out of the time series. Whereas in case of median, it's a single value. It is located close to mean. So they are statistically different measures. What I can tell you a little bit more technical. So if you calculate a mean value may differ from the actual values that you have, because it's a arithmetic sum and division. Whereas if you use a median always corresponds to a value that is in the time series. that's basically the difference. Mean also a little bit more susceptible to division problems. Sometimes the division by 0 is problematic, and that kind of things happens. Which one probably gives better images? So yeah, something being better is extremely subjective. So it really depends on your aim. So on your research question. So saying mean is better than median is not correct. So it really depends on the type of analysis that you are doing. So that you should check. So can we run customized band index like NDCI or TBD in the web editor? Yeah, that is possible. So as I showed you in the web editor, the wizard supports many different indices. So you can check if the index is already described there. In that case, you can use the wizard to create the index. Otherwise, you just need to create your index calculation in a reducer process. So you double click, and in the window that's opening, basically you create your process. What I will suggest you is to use the wizard to create an index, have a look how it is implemented, and modify it according to your equation. So I think that would be the easiest. Okay, yeah, I don't see any questions, and actually our time is also over. For further questions, of course, you can always contact me or EU Africa R&D facility. We have a discussion forum, so you can use the forum to pose your questions, and our experts or people from the EU Africa R&D community, they can help you. But OpenEO has also a forum that is available. So you can also use the forum to pose your questions regarding OpenEO. The good thing about that forum is that the developers of OpenEO are also members, so you can get first-hand support from the developers if you pose your questions into OpenEO forum. You can find the link on the OpenEO webpage. Okay, with this, I want to thank you for your participation. So I hope it was a useful webinar. So it is recorded. It will be available also after the event. So you can watch it at any time to see more information about OpenEO and how we use the web editor for creating. Thank you.